In this video, I introduce a way of policy batch deep reinforcement learning of implicit human preferences. Suppose that ST is the state at time t. The agent takes the action AT and the policy pi and receives the reward R. The agent maximizes the reward over trajectory tau with the future discount factor gamma. Q-learning learns the action value estimate of the total expected discounted future reward, defined as here, which is based on the Bellman equation here. A Q network approximates Q theta pi and drives the policy pi. To elevate overestimate bias, one target Q network computes the expected target reward Q theta t. As shown here, this current network, this target network. Target network uses action from a current Q network to calculate the Q that is user target in the current network. To perform a batch Q learning, a set of known environment trajectories is used to pre-train a generative model P, which generates the batch data via human interaction. The Q network and the target Q network are initialized from the pre-trained model as shown here. This batch Q learning model. This pre-trained model is used to generate batch data from human preferences. And then learn the policy pi. The learned policy pi is used for different kind of applications. The Q value estimate of state action pairs that are not covered in the batch data will be noisy, and this variance will lead the Maxwell operator to overestimate the value of these states. Batch Q learning obtains a distribution over predictions from the target Q network trained with dropout, and takes a lower band of this to reduce the overestimated bias. Batch Q learning Monte Carlo performs a dropout to approximate the posterior distribution P with the dropout distribution in QW, where W, X, Y are parameters input and output of the target Q network respectively. Given the target Q network Q theta T, the target state action value Q is computed by running M stochastic forward passes of the network using a Monte Carlo estimate of the lower band of Q theta T, defined as here. Where DI is a new dropout mask, the minimum operator here penalizes the high variance estimates and pushes the model to favor actions that lead to states well covered by the batch data. The KL control in Q learning incorporates the pre-trained prior into the policy, which is used to penalize divergence of the policy pi theta from the prior policy P, while maximizing reward R. Given trajectory of actions tau, the KL regularized objective is defined as here, where Q is a policy at the trajectory tau, P is the prior distribution over the trajectory tau. Using the definition here, the objective becomes to maximize the expected Q pi of the policy pi theta, as here, where P encourages the model to choose actions with a high probability and the prior, which biases the model to the action pairs that are realistic and likely to be in the batch. Negative log pi is entropy regularization for diversity in action space to prevent the solution collapsing to a small number of uninteresting samples. This is the workflow of KL control Q-learning model. For more details, please check with these references. Thank you. Bye.